We're now going to look at the third and final homologous series in this part of the topic, and that family of compounds is called the cycloalkanes. So very similar to the alkanes and alkenes in terms of naming that we've seen before, except this one has a cyclo in front of it. So what does that mean? Well, the cycloalkanes are just another homologous series. So we're looking for the same kind of things. We're looking for a general formula, we're looking for similar chemical properties, but this time it's a group of saturated cyclic hydrocarbons. So a few new words. Saturated we already know from our alkane homologous series family. We know that saturated just means all of the carbons that are involved and bonded together in these atoms, in these molecules I should say, are all singly bonded. Okay, so there's no double bonds, there's no unsaturation, they're all saturated. Saturated single bonds. But this time, instead of being in straight chains like the alkanes were, we now have cyclic hydrocarbons. So they still only contain hydrogen and carbon, that's not changed, but this time they are part of a cycle. So what does that mean? It means the carbon atoms bond in a way that forms a ring-like structure. So instead of being in a straight line, they start and finish in the same place, like a ring. They're all connected, round in a cycle, if you like. So what else can we say about them? Well, similar to what we looked at before, these are also used as fuels, and they're also commonly used as solvents. So we've not come across that before. That's a new property, which we will examine a little bit more closely later on. They're also insoluble in water, just like the previous two homologous series families that we looked at. And what we want to do for the cycloalkanes is similar to what we did for the alkenes. We want to try and figure out, based on looking at the first few members of this series, what the general formula might be. So what is our template for figuring out how many atoms are in each compound? So let's try and do that now. So what I've done is same as last time. I have drawn out a table with the name, the molecular formula, and the full structural formula, which remember showed us all the atoms, all the bonds, for the first few cycloalkanes. And before I reveal what the first one is, again I'd like you to have a little think. Based on what I've just told you, based on that we have to form a cycle, a ring, what is the first cycloalkane in the homologous series of cycloalkanes? In other words, how many carbons would it have to have, at minimum, to be able to form a ring? Well, the answer is cyclopropane. Now, why does it have to be propane? Why can't we have cyclomethane or cycloethane, which would make more sense because they're further down there. They have less carbons. Why can't we start there? Well, if we only had one carbon, we can't join anything up in a ring because it's got no other carbons to bond onto. So that's completely out. There is no such thing as cyclomethane. Cycloethane? Well, again, no, because if we only had two carbons, we can only join them in a straight line. Doesn't matter how we orient them, we cannot get a ring structure. So, if we want a ring, the minimum number of carbons I need to use is actually 3. Not 1 and not 2, but 3. So when I do that, and I join all of my carbons up in a ring, I end up with every carbon being bonded onto 2 other carbons. Which means there is enough room left, if you like, there is enough valency left on each carbon to bond to 2 more things. Or to bond another 2 times, because remember, the valency of carbon is 4, and that number 4 was very important. Every carbon has to have 4 lines, 4 bonds coming off of it for our structures to make sense. So in this case, and in all the cases for every cycloalkane, we have to have 2 hydrogens coming off of our carbons if it's in a simple ring like this. Which means I end up here with 3 carbons and 6 hydrogens. Okay, so if I move on and I use the exact same prefix structure as before, I end up going from propane to butane, and this time of course it's cyclobutane. So all I've done is add on another carbon, which means I now have 4 carbons in my ring. Again, they're all singly bonded to one another, it's a saturated compound, and onto each of those carbons I can add another 2 things so they get saturated with hydrogen atoms. And again, every carbon has 2 hydrogen atoms coming off of it. And I know that looks more like a square than a ring, but remember, by ring we just mean that the carbons basically start and end in the same place, like a cycle. You can take your finger, put it on the carbon, any carbon you like, in the ring, and go right round the page and come back to the exact same spot without taking your finger off of the carbon ring. So let's try and figure out that general formula then. So what I've done is I've drawn in the next member of the cycloalkane homologous series. It's called cyclopentane. And based on the name alone, pentane, pent, we can say that it must have 5 carbons in its structure. So that's all I've done. I've drawn them out in a ring. And as we discussed, each carbon is bonded onto 2 other carbons. So we already have 2 things bonded onto each carbon. So in order to get to 4, I simply have to go round and add on 2 hydrogens round each carbon, so that each carbon adds up to 4. And that's what I'm going to do just now. I'm going to fill those in. Because remember, when I'm drawing full structural formula, I have to show not just all the bonds, but all the atoms as well, so that my structure is very clear. And if we had to go backwards this time and say, okay, if I know the full structural formula, can I write the molecular formula? Yes, of course I can, because I can just count all the atoms I have of each element. So how many carbons do I have in total? I have 5. And how many hydrogens do I have in total? I have 10. Now this is interesting because it lets us figure out the general formula here, but we might run into a bit of a problem. So let's see what happens when we do that. So clearly, all I've done to figure this out is say, well, however many carbons I have, whether it's 3, 4, 5, to find out the number of hydrogens, all I've had to do is double that number. Double the number of carbons that I have to get to hydrogen. So that tells me, for my general formula for the cycloalkanes, for any n carbons I have H2n hydrogens, which seems absolutely fine. However, we already know that general formula from elsewhere. We have already seen this CnH2n for another homologous series that we have looked at. So if you remember back to the alkenes video, we decided that in an alkene, for however many carbons we have, we simply double that number to get the number of hydrogens. And we proved that. We proved that by drawing out the first few alkenes, and it worked. We've now just done the same thing with the same general formula for the cycloalkanes. So this leaves us in a bit of a situation, because now when we look at this general formula, we'll be asking ourselves, well, is it an alkene? Is it a cycloalkane? How would we know? Well, the answer is there's actually a test, a chemical test that we could do to prove which one of these we have, because they react slightly differently. However, before we get on to that, we need to define what this situation actually is, because this happens all the time in organic chemistry. This happens all the time with carbon chemistry, where we have compounds that have the same atoms, so the same number of carbons, the same number of hydrogens, but they're just arranged slightly differently, or the bonding is slightly different. The structure is slightly different. And there is a special word for that, which we will look at in the next video.